Let's see, everybody. Hopefully this is working. This is our first video in section 15.8, and I'm narrating over what I already wrote out and thought I was talking through as we were doing it. So let's see if we can make this work. Okay, so I'm trying to see if we're going to actually see some pictures being drawn out here. And it kind of looks like we are. Okay, cool. All right, here we go. All right, I guess I'm going to talk through this. So there's me drawing the XY plane. Now here's just some region, call it R, in the XY plane. All right, there I am, wasting time shading it in. This is some region, say, that we want to do a double integral over. And we could just call it R. I think I might have called it. Let's see. Did I call it something? I did. I called it R. Okay, cool. Okay, but maybe you don't like the looks of that region for integrating with respect to X and Y, and you would rather integrate with respect to some other variables. So the thinking is, maybe that region is a cousin of some other region in terms of some other variables. So we're using U and V. Okay, so there's some other region there. And that's not R, but it's how R looks if you saw R through the variables U and V. So we're shading it in. That's some other region. I think I called it G. There's an error with the highlighter. Did I call it G or not? I did. Okay, I called it G. Okay, fantastic. Now, G and R are related in that X depends on U and V, and Y also depends on U and V. So in other words, X is some function of U and V, and also Y is some other function of U and V. So here we're calling the function that tells how X depends on U and V, we're calling it G, and the function that tells how Y depends on U and V, we're calling it H. So that's the relationship. You say a U comma V over there in the UV plane, and that tells you an X and a Y over here. Now, if you break G up into nice, organized little rectangular pieces, like we do for the purposes of integrating, that mesh that we just drew on G corresponds to some mesh over there on R. So in other words, if you take those horizontal lines, the red ones in G, so those are lines where V is constant and U is changing. Well, if U is changing, then X and Y are probably changing. And so those horizontal red lines correspond to some lines over there in R, but there's no reason to believe they're horizontal. I mean, X and Y might both change once you feed those U and V's into the functions G and H. And similarly for the vertical lines, on the left side of the picture, in those vertical lines, each vertical line U is fixed and V is changing. But if you change V, X and Y will change. So maybe the mesh over in R that corresponds to that mesh on G looks like that. So any particular little patch over in R, so you see I've shaded in that green patch there, any particular patch came from some patch back there in G. So that little shaded red patch in G gets routed through these functions G and H to give you some other little patch, the green shaded one, over on the right-hand picture. And what we're trying to do is keep track of the area exchange rate between those patches. So, okay. I think what we want to do is zoom in on the little green patch so that we can try and figure out what the exchange rate is. Now, the patch it came from over on the left was just a rectangle, so its base is, say, delta U, and its height is delta V. And we want to see what happens over on the right when we build the new little patch in terms of x's and y's. So we're going to zoom in on that new little patch eventually here. And when we do, we'll try to estimate its area in terms of the area of the original red patch. So let's see if we zoom in at some point here. I think that's the next thing that happened. Oh, it looks like I'm re-emphasizing there that x and y depend on u and v. So that little red patch becomes the little green patch over there on the right. Man, this is pretty weird watching this and narrating over it. I feel like I could go way faster. It's all this dead space. I must just be rambling, I guess, in between parts of the picture. Okay, so here we are, finally. We're zooming in. So there's the little green patch. It is not a perfect rectangle. It's some sort of, I don't know, four-sided figure, but the sides could be slightly curvy. Here's me trying to shade in the whole thing in that greenish color. Okay, so as we're shading, our goal is to try to figure out what's the exchange rate between the original red area on the left and this new shaded in area in green on the right. Are they the same? Is the green one double? Is it half? All of the answers to those questions probably depend on the functions g and h that are transforming the red patch into this green patch. And to start to figure out exactly what that connection is, we're going to use some Calc 3. Okay, so the next thing we're going to try to do is we're looking back at the little red patch and we see it's kind of formed by those two vectors there, those little tiny vectors, one along the base and one along the left edge of the red patch. Those vectors correspond to, respectively, a small change in u and no change in v, that's the base, and a small change in v and no change in u, that's the left edge. Those vectors get transformed into tangent vectors to the, quote, base and edge of the new patch. Now, in the original right-hand picture, it almost looks like those little green vectors are exactly along the base and edge of the green patch, so that the green patch is a genuine rectangle. It's not. You can see on the zoomed in picture, those green vectors, they're close, they're tangent to the base and the left edge down at that common point. But they're straight, they're vectors, they're arrows. Whereas the base and left edge of our green patch are curvy. In any case, if you take those two green arrows and you use them to form a genuine parallelogram, the area of that parallelogram will be close to, but not equal to, the area of the green patch. So let's name those two vectors. Looks like we're calling them W1 and W2. Now, we have to bust out some Calc 3 here. If you wish to know the area of the parallelogram spanned by W1 and W2, well, we know how to do that from Calc 3. It's going to be some kind of a cross product. So let's think about these two vectors, W1 and W2. Focus on W1 first. What is W1? W1 is laying flat in the xy plane and is generated by a small change in u and no change in v. Now, x and y will both change over that small change in u and no change in v. The rate at which x changes over a small change in u and no change in v is a partial derivative. It's dg du. So you take x's partial with respect to u. That tells you the rate of change. And then you multiply that by a small change in u, and that tells you the small change in x. So the x coordinate of that vector w1 should just be dg du. Whoa, look at that timing. Getting dialed in. Times tiny little change in u. Delta u. Delta u. Come on, Retzik, get on with it. Likewise, the second entry in W1, well, that should be the rate of change of y with respect to u, so dh du times some tiny little change in u. So there's the 2D sense of that vector W1. Now W2, that vector came from u being fixed and v changing by a little bit, so you can imagine it's just going to be same thing, only partials with respect to v times tiny change in v in each of the entries. So we've identified W1 and W2. Here's what's weird though. We said we wanted to cross them in order to get the area of that parallelogram. Well, this makes no sense as written. You don't cross 2D vectors. You only cross 3D vectors. Okay, well, these vectors are laying flat in the xy plane, so let's just call their third coordinate 0. So we're going to cross them. So the area of the parallelogram I threw the 5th grade spelling bee on the word parallel. I threw it on purpose because I had a crush on Jennifer Mazer. And it was down to Jennifer and me in the spelling bee. And I knew parallel because I had practiced it, because I knew the two L's in the middle of parallel are parallel. So I knew that's where the double L went. And then, I don't know, I just, I couldn't pull the trigger. Anyway, we need to cross W1 and W2. Fun Retzik facts for voiceover narration. We need to cross W1 and W2. So we need to think of them as 3D vectors. And since they're flat in the xy plane, let's just think of their third coordinate as 0. Then if you cross them, so you guys gotta go, do the cross product, dig that thing up from Calc 3. But I can tell you, if you cross them, you will get a third vector. That vector will have only a k component. So that vector is pointing straight up. You guys know that. When you cross two vectors in the xy plane, it points straight up. When the dust settles, if you do the cross product of those two vectors, W1 and W2, it comes out to dg du dh dv minus dg dv dh du, all times delta u delta v, all in the k direction. And then we want the magnitude of that, but k is a unit vector. So the magnitude of that is simply the absolute value of dg du times dh dv. Take away dg dv times dh du. All times delta u, delta v, those are positive, so they don't have to be inside the absolute value. So that's the length of that vector. Okay. So that piece, the area of that parallelogram, that's roughly the tiny little delta A. Where? Which side of the picture? That's happening in XY land. You see that little green patch? It's on the XY side of the picture. So that's happening in XY land. I made a mistake there. That's funny. XY land. Good. I was going to say, come on, man. Now that little piece right there, delta U, delta V, where is that? That's delta A in UV land. Those are the dimensions of the little red patch. And that piece is somehow the correction factor. So the area of the patch in XY land is not literally equal to the area of the patch in UV land. It's this weird thing with partial derivatives times the area of the patch in UV land. Now that notation right there, you guys, it's just pixels. It does not mean anything. If you're looking at that like, whoa, what kind of partial is that? No, it's nothing. It's not any kind of partial. It's just the symbol we use for that expression inside the absolute values. And that's called the Jacobian. And it's named after a mathematician from a few hundred years ago named Jacobi. A Swiss mathematician, I think. Anyway, that's just our symbol for the Jacobian. Okay, so now I can see that we're at the 3 minutes to go mark or so. So now all we're trying to do is figure out what all this analysis has to do with double integrals. Okay, so I'm going to scroll down probably in a second. Yeah, so that thing, that correction factor, that's called the Jacobian. Okay, so we need to know the point now. Oh, the point. Look at that. I must think just like the guy who made this video in the first place. All right, here's the point. If you're trying to do a double integral over R, over there in XY land, so you got some function with x's and y's in it, and you're doing it, say, dx dy. If you wish to compute that integral, but in terms of the letters u and v, well, in terms of u and v, you're integrating over g. And everywhere you see an x, you got to put little g of uv. And everywhere you see a y, you got to put little h of uv, because that's what x and y are in terms of u and v. And then the dx dy, we just argued the dx dy becomes Jacobian times du dv. So this is just our symbol for Jacobian. And now the new letters of integration are du dv. And that is the point. If you change variables on a double integral from x's and y's into u's and v's, you gotta keep track of that area exchange rate. And the way you keep track is through the Jacobian. Okay, so today's video, this was to give us the motivation behind what that Jacobian factor is and where it came from. Your book says something funny. It says something like, The development of the Jacobian belongs in a much harder class than this one, so we're not going to do it. Well, I mean, I sort of agree, but also it's not that bad, and it does use that Calc 3 idea of approximating the green patch with a parallelogram. The area of that parallelogram comes from crossing those two vectors, W1 and W2. So it's all geometry, and the Jacobian is the ticket. All right, in tomorrow's video, we're going to do examples. Knowing what this is and where it comes from is one thing. Doing problems is another entirely. Okay, see you next time.